Thank you for inviting me to this, to present this paper and selecting it to be presented. I'm Richard Austin. I'm President and Chief Technology Officer of Gamma Scientific, and I am going to be talking about neurodisplay technology that was developed at Gamma Scientific. Specifically to measure near-eye displays, augmented reality, virtual reality displays. We have a long history of measuring virtual images from displays, specifically heads-up displays for military and commercial programs. The F-16, F-18, B-1B, F-117, C-17, and F-35 are all military displays that we've measured for over 40 years. For AR, VR, and heads-up display, the important thing is the ability to measure light from different angular directions in the virtual image field of view. The Gamma Scientific near-eye display measurement system draws on our decades of experience to measure these particular types of virtual images. So there's many types of near-eye displays: augmented reality and merged reality, helmet mount displays, and virtual reality, where the display is the only thing that the viewer sees. There's minimum requirements for measuring accurate luminance and color in near-eye displays, and the first, probably most important requirement is the entrance pupil must be positioned in the design eye box, or also referred to as the qualified viewing space. Entrance pupil diameter of the measurement telescope also must be smaller than the qualified viewing space, and so the entrance pupil of your measurement system must be overfilled by light in the qualified viewing space, and entrance pupils on the order of 3 to 5 millimeters mimics the human iris size when these displays are being used by people. Most display spectrodiometer systems have a much larger entrance pupil on the order of 20 to 40 millimeters, and taking this down to 5 millimeter reduces the light by 16 to 64 times. Light measurement system must have enough sensitivity and dynamic range to provide adequate signal and noise to make accurate luminance and color measurements. The ability to point in different directions, as I said earlier, is really the key. XY translation only moves you within the qualified viewing space and doesn't allow you to point to different directions of the virtual image space. So the axis of rotation must be in the qualified viewing space in order to see the extents of the visual field of view. Excuse me. So additional requirements are you have to have a compact size so that the measurement system can position its entrance pupil of the spectrodiometer system or photometer at the design eye location. You have to have a small entrance pupil diameter. You have to have high sensitivity and high dynamic range for good signal and noise. You have to have exceptional color measurement spectral purity for laser-based displays, where the primaries that produce the color in color space are very narrow, so highly saturated. So spectral purity is important. If you don't have it, you get very large errors in the setting of the white point. The ability to point in different directions in different areas of the virtual image field of view is required also. And the CAM is camera. So the radomacam is coupled via fiber optic probe to the spectradiometer, which has very high spectropurity and very good sensitivity using a scientific grade backside thin CCD sensor. And then the device under test, the radomacam telescope and the spectradiometer are all controlled by the system controller, as well as the 6-axis robot is controlled by the system controller. And there's an optional tunable light source that can produce different daylight or fluorescent spectral power distributions to provide background contrast measurements for AR displays. And then there's an optional autocollimating reference mirror that's used as the reference between the left and right eye positions of the radomacam for parallax measurements. The GS1290 near-eye display spectradiometer system is shown here looking at a flat panel display. So we took the radomacam telescope that we've been producing for about a decade and adapted it to make it even smaller to fit within the human head profile here. This is our buddy Harry, and it shows the entrance pupil of our telescope positioned at the design eye point or center of the qualified viewing space. The fiber optic probe connects to the spectradiometer here. So the software that controls the whole system is modular as well. The 6-axis robot positioning of the radomacam is controlled via the software interface. The detector, spectradiometer, flicker measurements are controlled through the software. The telescope optics, the selection of the measurement aperture is controlled, as well as the internal pattern generator software and internal pattern generator electronics in the system controller to display different test patterns on the device under test. The near-eye display variable field of view telescope, the radomacam, is lightweight and compact for fast positioning. With when attached to a robot arm, there's an integrated color or optional monochrome CMOS camera for image processing in the viewing area under test. Excuse me. And alignment to the specific area that you're measuring. There's a proprietary single lens reflex viewing system with an integrated LED that projects the measurement spot. So this is an actual projection of the actual measurement aperture. So there's an unambiguous definition of the measurement aperture. This allows for autocollimation to a mirror target for parallax measurement. And there's also 6 different field of view apertures built into the telescope. So the optical system is configured when configured in the view mode, has the light comes in from the object and reflects off the beam splitter and forms an image on the image sensor plane. So you have an image of the object that you're trying to measure. And when this beam splitter is in the optical path, there's an LED that's behind the measurement aperture that projects light out through the measurement aperture, which is perpendicular to the optical axis, reflects off the back, recombines, and focuses it and superimposes an image of the measurement aperture onto an image of the object. So the field of view aperture is selectable. There are 6 different field of views from 5 degrees down to 1/10 of a degree, and the Viewfinder camera is also used for processing the image from the object. In the spectroradiometric measurement configuration, the beam splitter, which is positioned here, and the LED that's behind the measurement aperture is moved out of the way, and you have a clear optical path with no polarization optics between the objective lens and the collection aperture, which is the fiber optic connection to the spectradiometer. This field lens or relay lens system serves a dual function in collecting all the light that passes through the field stop and getting it to the aperture, but it also defines this physical entrance pupil as the optical entrance pupil also. So this whole optical system defines the entrance pupil right here at the physical stop of the entrance optical system. The different measurement areas for the spectroradiometer are shown in these captured images of the viewing system camera, showing a standard resolution color test target from the IDMS document. So we have a 5 degree, 2 degree, 1 degree, half degree, third degree, and 10th of degree or 6 arc minute measurement spot. So this shows that the limits of our spectroradiometric measurement capability are at the threshold of the visual acuity area. So the total field of view of the viewing system, which is also can be used for image processing, is 7 by 7 degrees or 10 by 10 degrees, depending on the CMOS image sensor that's in the viewfinder. So this is overlaid over the whole field of view that can be seen through a typical augmented reality display like the BT200s that we have data system. So the 6-axis robot and the small mass and size of the Robotic is very convenient to point to different directions of the virtual image field of view. For the data presented in this paper, we have a 5 by 7 array of different pointing directions that we pointed to in the visual field of view, and we rotated about the entrance pupil or near the entrance pupil to pivot in the qualified viewing space to get luminance, color differences, white point differences, correlated color temperature, dominant wavelength, and any information that we can extract from the spectroradiometric data. So the results that we obtained using this system for the augmented reality sample data for Epstein.
In this video, we show the automated robot-mounted near-eye display measurement system
Robotic telescope
measuring the
that
same
can move between right and left eye position.
augmented
And we have
reality
programmed
glasses
here
shown
to
in
look
previous
at 9
video
different
measurement system
locations
setup.
rather than the 27 for the data. And this is to illustrate how the pivot point
The telescope,
is
mounted to the
center of
industrial
the
robot,
entrance pupil
can
of the
easily
telescope.
move between the
In this
left
case,
and right eye positions with
can
high
easily move between the left and right eye
and
position
accuracy.
and easily point to different directions. It's making a spectroradiometric measurement
The pivot
of the
point
virtual
for the
image
measurement
field of view
telescope
that was shown
optical
in the
axis
previous
direction
slides,
is programmed
and
into the industrial robot's coordinate
can
system,
quickly
which assures
acquire
that the spectroradiometer entrance pupil
a
is
lot of
centered
data
in the design eye
at
box
each location.
display.
It's also
head-up display
acquiring
measured
a
color. Precise positioning within the design eye box
image
is
of
essential
the
for repeatable and
what's shown in the
reproducible
field of view
measurement
when
results.
the LED is turned off and captures that image and can be later processed for uniformity within the image and tie the data from the spectroradiometric data. So two different the robot allows for easy configuration between the rotation point being either the entrance pupil of the spectroradiometer or the center of the eyeball, so the design eye. So this can be 13 millimeters back from the entrance pupil, can be selected as the vantage point, and the entrance pupil of the spectroradiometer and image processing camera will rotate as the human eye iris would rotate relative to the qualified viewing space of this display. So the system software controller this is the interface panel, and there's separate modules for controlling the robot or the spectroradiometer or the graphics generator that can all be controlled with this display measurement control panel. Each of the modules are connected with the main module through a TCP protocol. So the image processing, the robot, the spectroradiometer, and the graphics generator are all spectroradiometric measurement taken at these 27 different or 35 different pointing directions. So this to this plot. So this is 231, 230, and 290, and they're shown here in these three plots. So this is measured from the center of the qualified viewing space. We can also determine the white point or color uniformity. Oh, I'm sorry. The luminance measured in this 1 degree field of view is tied to the 8.9 megapixel color image, and so the area shown within this can be determined, the uniformity can be determined in an even finer resolution than this spot in this image. So this uniformity area here, the luminance can be determined over this whole area. So we can do the same sort of thing for color uniformity. So this is the data based on the spectroradiometer of the correlated color temperature of the display at those 35 different locations. And this is the plot showing the range of correlated color temperature change or white point. So there's over 150 degree Kelvin change in the white point in this uniform field in the BT200s. The image captured with the integral CMOS 8.9 megapixel CMOS sensor can be analyzed for depth of modulation, and we apply the IDMS section 7.2 methodology, where there's a moving weighted aperture filter that goes through and smooths out the individual pixels, and the standard methodology then determines a reproducible image contrast measurements between the peak and the trough in this ratio. So looking at the resolution of the CMOS image sensor relative to the pixels on the display, we can see that there's plenty of resolution in the camera to get very high resolution depth of modulation measurements over this 7 to 10 degree square field of view that we have with our CMOS image sensor. So this is more detail of the modulation transfer depth of modulation measurement. So the difference between the peak and the trough here before the moving weighted average aperture is applied is shown as 57%, and then it goes down to 37% depth of modulation for white, dark, white line in this case. And we can also rotate the image. We have full control over the analysis. So in summary, Gamma Scientific's near-eye display measurement system is a very unique and comprehensive system. It can acquire very repeatable and reproducible low uncertainty measurements in control of production testing for NEDs. The hardware system and software is modular, can be easily configured for various types of NED measurements. The image processing module can be a standalone camera. So it's quite flexible. Thank you very much for your time.